What if I told you that thousands of years ago, ancient civilizations could pinpoint the positions of stars with jaw-dropping accuracy without a single telescope, computer, or modern tool? Picture this: a Babylonian astronomer in the dusty glow of an oil lamp, etching precise celestial coordinates into clay tablets under a sky ablaze with stars. Or Greek scholars mapping the heavens with such detail that their work still baffles historians today. These aren't just stories, they're real, tangible records left behind by cultures who saw the cosmos not as a distant mystery, but as a living map etched into the night. And here's the thing: the more we study these ancient star catalogues, the more they seem to defy everything we thought we knew about the limits of early astronomy. Across 40 different catalogues, from the banks of the Euphrates to the libraries of Alexandria, our ancestors documented the heavens with a precision that feels almost supernatural for their time. How did they do it? What drove them to spend lifetimes tracking the slow dance of stars and planets? Some of these records are so accurate that modern astronomers have used them to trace cosmic events that happened millennia ago. But the real shock isn't just the technical skill, it's the burning question behind it all. Why? Why did these cultures, separated by continents and centuries, share such an obsessive drive to chart the skies? The answers might rewrite what we think we know about human ingenuity, the passage of knowledge, and our timeless connection to the stars. This journey isn't just about astronomy, it's about peering into the minds of the past. Imagine holding a clay tablet inscribed by someone who gazed at the same stars you see tonight, but through a lens of myth, mathematics, and sheer wonder. These catalogues aren't dry lists of data. They're love letters to the cosmos, left behind by people who believed the heavens held secrets worth sacrificing lifetimes to uncover. And as we unravel their work, you'll start to see the night sky the way they did, not as a backdrop but as a story, one that connects every one of us across time and space to something far greater than ourselves. So let's step into their world, where the line between science and magic blurs, and where the stars still whisper secrets waiting to be heard. To understand why these ancient star catalogues matter, we have to step into the shoes of the people who created them. Think about the Babylonians, who didn't just see stars as distant lights, they saw them as gods, omens, and even road signs for trade routes stretching across deserts and seas. Their famous Emuel, pin tablets etched around 3,000 years ago, didn't just list stars, they tied them to planting seasons, flood predictions, and even the reigns of kings. It was astronomy woven into the fabric of daily life, where a shift in the sky could mean the difference between a bountiful harvest and famine. Then there's the Greeks, who took stargazing to another level. Hipparchus, working in the 2nd century BC, didn't just note star positions, he ranked them by brightness, a system we still use today. His catalogue was so precise that when modern astronomers compared it to digital sky maps, they found discrepancies of less than 1 degree. How? Some speculate he had access to even older Babylonian records, now lost to time. Others wonder if he used tools we haven't yet rediscovered, instruments so advanced they vanished with the Library of Alexandria. And let's not forget the Chinese, whose star maps were so detailed they included nova and comets, events most cultures dismissed as fleeting anomalies. The Dunhuang star chart, dating back to the Tang dynasty, plots over 1,300 stars with stunning accuracy, centuries before Europe's first telescopic observations. What's fascinating isn't just the precision, but the purpose. For the Chinese, the heavens were a mirror of earthly order, a celestial blueprint for emperors and scholars to decode. A supernova recorded in 1054 wasn't just a celestial event, it was a cosmic memo, a sign demanding interpretation. But here's what ties these cultures together: necessity. Whether it was the Babylonians predicting floods, the Greeks navigating the Mediterranean, or the Chinese aligning imperial rituals with the stars, their catalogues were survival tools. They didn't track the sky out of idle curiosity, they did it because their lives depended on it. And that's the real magic of these records. They weren't just scientific achievements, they were acts of devotion, desperation, and sheer human ingenuity. Every star plotted was a step toward taming the chaos of an unpredictable world. So when we look at these catalogues today, we're not just seeing data, we're seeing the birth of science itself. A relentless drive to make sense of the unknown, written in clay, parchment, and stone. And the most haunting question isn't how they did it, but what else they knew that didn't survive the flames of war, time, or forgotten libraries. These catalogues are fragments of a much larger conversation, one we're still trying to piece together. Long before telescopes or computers, the Babylonians were mapping the night sky with a precision that still leaves astronomers speechless. Their star catalogues, etched into clay tablets over 3,000 years ago, aren't just simple lists, they're intricate celestial almanacs, blending astronomy, mythology, and advanced mathematics. Take the Apin tablets, for example. These weren't just star charts, they were cosmic calendars, linking the movements of constellations to the rhythms of agriculture, politics, and even religion. When a certain star rose before dawn, it signaled the time to plant barley. When Venus appeared in a specific position, it might foretell the fate of a king. This wasn't just stargazing, it was a survival manual written in the stars. What's truly mind-blowing is how they predicted lunar eclipses with remarkable accuracy. Without lenses or precise instruments, they spotted patterns in the chaos. By tracking the Saros cycle, a repeating 18-year pattern of eclipses, they could forecast celestial events decades in advance. How generations of scribes meticulously recorded every anomaly, building a database of cosmic rhythms passed down through oral tradition before being immortalized in clay. Some tablets even include error margins, showing they understood their predictions weren't perfect, a shockingly modern grasp of scientific uncertainty. But here's the real kicker: their math was so advanced it feels out of place in history. They used a base 60 number system, the reason we still divide hours into 60 minutes and circles into 360 degrees. Their calculations for planetary motions were so precise that later Greek astronomers like Ptolemy borrowed directly from their work. And let's not forget the 3 stars each system, dividing the sky into 3 parallel paths tied to specific gods. This wasn't random mythology, it was a sophisticated coordinate system, a celestial grid etched into the fabric of their worldview. Yet for all their brilliance, we've only recovered fragments of their knowledge. Most Babylonian tablets were lost to wars, fires, or the slow erosion of time. What survives hints at a vast, interconnected web of observation, one that might have included star maps far older than Apin. Some scholars speculate they inherited data from even earlier cultures like the Sumerians, whose astronomical insights vanished with their cities. It's a haunting thought. How much more did they know? Their legacy, though, is undeniable. When Greek astronomers like Hipparchus began mapping the heavens centuries later, they stood on Babylonian shoulders. Even Islamic scholars of the Middle Ages revered these ancient tablets, translating and expanding their star catalogues. The Babylonians didn't just watch the sky, they decoded its patterns with a rigor that laid the groundwork for all of Western astronomy. And that's the real wonder. Their work wasn't just for their time, It was a bridge across millennia, a testament to human curiosity so relentless. It turned the chaos of the cosmos into something we could measure, predict, and ultimately understand. Hipparchus didn't just observe the stars, he revolutionized how we see them. Working on the Greek island of Rhodes around 129 BCE, this solitary astronomer did something unprecedented. He mapped the heavens with mathematical rigor, assigning precise coordinates to over 850 stars. His catalogue wasn't a mere list, it was a cosmic grid, a blueprint so accurate that when modern astronomers cross-checked his data, they found errors of less than 1 degree. That's like pinpointing a single grain of sand on a beach without a telescope. How? Historians suspect he relied on instruments like the armillary sphere, an intricate ringed device that could track a star's path across the sky. But here's the twist: Hipparchus didn't work in isolation. He built on centuries of Babylonian records, merging their raw data with Greek geometry to create something entirely new, a fusion of myth and math. Ptolemy took this even further. 2 centuries later, his Almagest became the astronomical Bible of the ancient world. This sprawling text didn't just catalogue stars, it laid out a complete model of the universe, with Earth at the center and planets moving in perfect circles. While we now know that model was flawed, its precision was staggering. Ptolemy's star positions were so reliable that sailors and scholars used them for navigation well into the Renaissance. But what's often overlooked is the philosophy behind his work. To Ptolemy, the heavens weren't just mechanical, they were divine. Each star's motion reflected a harmony that echoed Plato's ideals, blending science with spiritual awe. Yet for all their brilliance, these catalogues hold a tantalizing mystery. Both Hipparchus and Ptolemy wrote of even older star maps, records from lost civilizations like the Chaldeans or Egyptians that may have contained data far more advanced than anything surviving today. Some scholars argue that Hipparchus's famous discovery of the precession of the equinoxes, the slow wobble of Earth's axis, could only have been detected using observations spanning centuries. Who provided those observations? The answer might lie in libraries that burned long ago. The legacy of these Greek astronomers isn't just in their charts, it's in their method. They didn't just record the sky, they questioned it. When Hipparchus noticed a new star appearing in Scorpius, likely a supernova, he didn't dismiss it as an omen. He revised his entire catalogue to include it, setting a standard for scientific adaptability that still inspires astronomers today, and that's the real wonder of their work. It wasn't frozen in time, it was alive, evolving, and above all, human, a testament to the relentless curiosity that turns starlight into understanding. Now, imagine crossing continents to an empire where astronomy wasn't just science but statecraft. While the Greeks mapped the Mediterranean skies, Chinese astronomers were weaving the stars into the very fabric of imperial power, with star catalogues so detailed they'd make even Ptolemy pause. In the courts of ancient China, astronomy wasn't just a science, it was the heartbeat of empire. The Dunhuang star chart, painted on silk around the year 700, isn't just a map of the cosmos, it's a masterpiece of bureaucratic precision. Imagine scribes in towering observatories, tracking every flicker of light across the night sky, knowing their records could decide the fate of dynasties. With over 1,300 stars plotted in meticulous detail, this chart wasn't about curiosity, it was about control. Emperors believed celestial events mirrored earthly power, so a shooting star wasn't just a spectacle, it might signal rebellion, drought, or divine favor. What set Chinese astronomy apart was its sheer institutional might. While Greek scholars worked in isolated brilliance, China had entire bureaus of astronomers, their observations funded by the state. Stargazing towers dotted the empire, staffed by officials who tracked comets, sunspots, and even the explosion of the Crab Nebula in 1054, a supernova so bright it was visible in daylight for weeks. Their records were so precise that modern scientists still use them to study cosmic events today. But the real genius lay in their tools. The armillary sphere, a complex ringed instrument, could measure star positions to within fractions of a degree. And their equatorial coordinate system, dividing the sky into 28 lunar mansions, was so advanced it predated similar Western systems by centuries. Unlike the Greeks, who saw the heavens as geometric perfection, the Chinese treated them as a living clockwork where every shift had meaning. A planet out of place wasn't just a puzzle, it was a portent demanding imperial action. Yet for all their rigor, there's a haunting gap in their records. Many star maps were destroyed in wars or purges, their secrets lost to time. The Dunhuang chart survived only because it was hidden in a sealed cave for 1,000 years. What else might have vanished? Some scholars speculate that Chinese astronomers knew of Jupiter's moons long before Galileo, but without telescopes, how? The answer may lie in their relentless patience, watching the same stars for generations until patterns emerged no single lifetime could reveal. This obsession with the sky wasn't unique to China, though. Halfway across the world, another civilization was weaving stars into the fabric of daily life, not for emperors but for faith. As the Tang dynasty flourished, Islamic scholars in Baghdad were rescuing lost Greek and Babylonian texts, adding their own breakthroughs to the celestial puzzle. Their star catalogues wouldn't just preserve ancient knowledge, they'd refine it with instruments like the astrolabe, turning navigation into an art form. And in doing so, they'd bridge the gap between the old world and the new, one star at a time. While Europe navigated the so-called Dark Ages, a revolution was unfolding under the domed observatories of the Islamic world. Picture the scene. In the bustling House of Wisdom in 9th century Baghdad, teams of scholars pored over crumbling Greek and Babylonian manuscripts, translating Ptolemy's star charts while simultaneously correcting their errors. Among them stood al-Sufi, whose book of fixed stars didn't just copy ancient knowledge, it refined it. When he noticed discrepancies in Ptolemy's work, he didn't dismiss them as scribble errors. He grabbed an astrolabe and measured the stars himself. The result, a catalogue that added detailed descriptions of nebulae like the Andromeda Galaxy, a fuzzy patch he called the Little Cloud, centuries before telescopes would reveal its true nature. But the real game changer was institutional support. While Greek astronomers often worked alone, Islamic science thrived under the patronage of caliphs who saw the stars as both divine signs and tools of empire. The Maraghe Observatory in Persia, funded by Hulagu Khan himself, boasted instruments so massive they required teams of mathematicians to operate. Their star tables, like the Zij-i-Ilkhani, didn't just list positions, they accounted for atmospheric refraction, a subtle distortion of starlight that even Ptolemy had missed. And in Samarkand, Ulugh Beg built a 3-story sextant so precise it could measure angles down to seconds of arc, all to create a catalogue that rivaled Tycho Brahe's work 2 centuries later. What made their instruments so extraordinary? Take the astrolabe, a handheld computer of brass and engraved coordinates. Unlike simple quadrants, it could solve hundreds of astronomical problems, from finding prayer times to predicting eclipses, with a twist of its dials. But the secret sauce wasn't just technology, it was methodology. Islamic astronomers introduced systematic error checking, repeating observations over decades to weed out mistakes. When al-Battani recalculated the length of the solar year, his result was off by just 2 minutes, a leap forward from Ptolemy's 30-minute error. Yet for all their precision, these scholars never divorced science from spirituality. The same astronomers who mapped the stars' paths also wrote poetic treatises on the cosmos as a manifestation of divine order. Their catalogues weren't cold datasets, they were bridges between faith and reason, where mathematics revealed the harmony of creation. And when their works reached Europe via translated manuscripts in 12th century Toledo, they ignited the Renaissance, proving that knowledge, once preserved, has a way of outliving empires. Now consider this: many Islamic star catalogues referenced even older sources, texts from Alexandria, Babylon, or Haran that vanished long ago. Some scholars speculate they contain data from lost observatories or forgotten celestial events. It's a reminder that every ancient catalogue we've explored is just a fragment of a far grander conversation, one that stretches back to the first time a human looked up and dared to measure the immeasurable. The precision found in ancient star catalogues doesn't just defy expectations, it shatters them. Take Hipparchus's measurements, accurate to within a single degree. To put that in perspective, imagine trying to pinpoint the exact location of a candle flame from over a mile away, using nothing but your naked eye and a rudimentary wooden tool. That's the level of exactitude we're talking about. How did they achieve this without lenses, without precision gears, without any of the technology we consider essential for astronomy today? One theory points to reflective pools. Picture an ancient observatory where still, dark water acts as a natural mirror, sharpening the star's reflection and making it easier to measure angles against fixed landmarks. The Greeks and Babylonians both wrote of using liquid surfaces to study the heavens, turning something as simple as a basin of water into a proto-telescope. Others speculate about water clocks, not just for tracking time but for synchronizing observations across nights, allowing astronomers to build cumulative data over years or even decades. Then there's the possibility of lost tools, instruments sophisticated enough to rival early Renaissance devices but destroyed or forgotten over time. The Antikythera mechanism, a 2,000-year-old Greek device often called the world's first computer, proves they had the engineering prowess to create intricate gear systems. Could there have been others, perhaps even more advanced, that didn't survive the collapse of their civilizations? Some researchers argue that devices like the dioptra, a sighting tube used for land surveying, might have been adapted for celestial measurements, offering a level of precision we've underestimated. But perhaps the most compelling explanation isn't technology at all, it's sheer, grinding persistence. Generations of scribes meticulously recording the same stars, cross-checking each other's work, refining their methods over centuries. The Babylonians, for instance, kept detailed logs of Venus's positions for over 600 years. That's not just dedication, it's institutional memory on a scale most modern scientists can't fathom. Imagine an unbroken chain of observers, each building on the last, until patterns emerged that no single lifetime could reveal. And yet, even these explanations don't fully account for the anomalies. Some star positions in ancient catalogues align too perfectly with modern data to be coincidence. Could they have inherited knowledge from even older, now vanished cultures? The Greek historian Herodotus wrote of Egyptian priests who claimed their astronomical records stretched back tens of thousands of years. While that's likely exaggeration, it hints at a truth we're still piecing together. These catalogues might be fragments of a far older tradition, one that viewed the sky not as a mystery to solve, but as a language to be memorized. What's undeniable is the ingenuity behind these achievements. Whether through tools, patience, or lost wisdom, ancient astronomers turned the night sky into a mathematical masterpiece. And that raises a tantalizing question. If they could map the stars with such precision, what else did they understand about the cosmos that we're only beginning to rediscover? Next, we'll see how mythology wasn't just storytelling. It was a framework for understanding the heavens, woven into the very fabric of these star catalogues. For these cultures, the sky wasn't just data, it was a living story, and every star had a role to play. To the ancient Babylonians, the stars weren't just points of light, they were the handwriting of the gods. Every flicker, every constellation carried a message. When they looked at the Pleiades, they didn't see a random cluster. They saw the 7 sisters, celestial markers that signaled the start of the agricultural year. This wasn't just poetry, it was practical cosmology. Myths gave order to the chaos of the night sky, turning abstract patterns into stories so vivid, anyone could remember them. Imagine a shepherd gazing up at Orion, not as a collection of stars, but as the hero Gilgamesh, striding across the heavens with his club raised. These narratives weren't decoration, they were memory aids woven into the very fabric of early astronomy. The Greeks took this even further. For them, the sky was a grand stage for their myths. The constellation Andromeda wasn't just a celestial shape, it was a princess chained to a rock, rescued by Perseus, her story forever etched among the stars. These tales did more than entertain, they encoded knowledge. Sailors navigating the Aegean could find their way by following the myth of the Great Bear, Ursa Major, whose tail always pointed north. The stars became a storytelling compass where every turn of the sky revealed another chapter of human experience. But here's what's fascinating, these myths crossed cultures. The Babylonian dragon Tiamat, slain by the god Marduk, finds eerie echoes in the Greek tale of Zeus defeating Typhon. Were these stories coincidence or evidence of an older, shared astronomical tradition? Some scholars argue that myths acted as a prehistoric internet, transmitting celestial knowledge across generations before writing existed. A constellation's name might change, but its role as a seasonal marker, like Sirius heralding the Nile's flood, remained constant, binding science to survival. Yet mythology's greatest gift to astronomy was its humanity. By tying the stars to gods, heroes, and animals, ancient cultures made the cosmos familiar. The sky wasn't a cold, distant void. It was a mirror reflecting human fears, triumphs, and questions. When a Greek farmer saw Cassiopeia's throne in the heavens, he didn't just see stars. He saw a queen punished for her vanity, a moral lesson written in light. This emotional connection transformed astronomy from a dry study into a shared cultural legacy, one that resonated across campfires, temples, and royal courts. And that's the real magic of these star catalogues. They weren't just technical manuals, they were the first textbooks of human curiosity, blending observation with imagination. The same impulse that led the Babylonians to track Venus's movements also inspired them to call it the goddess Ishtar, weaving mathematics and myth into a single tapestry. Today, we might separate science and story, but for them, the two were inseparable. The stars didn't just guide their ships, they guided their understanding of who they were. Now picture a Phoenician trader on a moonless night, steering his ship by the same stars that told his ancestors' stories. The line between myth and navigation blurs here because for him, the constellations weren't just maps, they were companions. As we'll see next, these celestial stories didn't just live in temples or tablets. They sailed across oceans, turning the sky into the world's first GPS. Long before compasses or satellites, the stars were humanity's first highway signs, guiding ships through uncharted waters with nothing but the night sky as a map. Picture a Phoenician merchant vessel cutting through the Mediterranean's dark waves, its captain squinting at the North Star, Polaris, to stay on course. Unlike other stars that wheeled across the heavens, Polaris held steady, a fixed beacon that told sailors their latitude. To drift too far from its guiding light meant risking shipwreck or worse, vanishing into the unknown. But the Phoenicians weren't just stargazers. They were master navigators who turned constellations into a celestial road atlas, memorizing star patterns to link ports from Tyre to Gibraltar. Half a world away, Polynesian voyagers achieved something even more astonishing. Without written star catalogues, they crossed thousands of miles of open Pacific by memorizing the star paths, sequences of rising and setting stars that acted like celestial waypoints. Each star was a stepping stone. When one vanished below the horizon, another would rise to take its place, creating an unbroken chain of guidance. They didn't just navigate by stars, they felt the ocean's swells, watched bird flight patterns, and even sensed disturbances in cloud formations. Their knowledge was so precise that modern recreations of their voyages, using only traditional methods, have landed within sight of tiny, remote islands. How, through an oral tradition so rigorous it turned the night sky into a living, breathing compass, medieval Arab traders, armed with al-Sufi's star catalogues, took this celestial navigation to new heights. Crossing the Sahara or sailing the Indian Ocean, they relied on instruments like the camel, a simple wooden card tied to a string, to measure a star's angle above the horizon. But the real genius was in their memory techniques. They didn't just memorize star positions, they wove them into poems and stories, turning dry coordinates into rhythmic verses easy to recall during long, lonely journeys. A single line of poetry might encode the rising of Sirius or the position of Orion's belt, blending science with artistry. Yet the star's role didn't end at the shoreline. Inland, farmers from Mesopotamia to Mesoamerica planted their crops by celestial cues. The Egyptians timed the Nile's floods by the heliacal rising of Sirius, when the star first reappeared after months hidden by the sun's glare. For them, this wasn't just astronomy, it was agriculture by celestial decree. The Maya, too, tracked Venus with eerie precision, believing its cycles dictated the best times to plant maize or wage war. Their Dresden Codex contains Venus tables accurate to within 2 hours over 500 years, a feat that still stuns modern astronomers. What ties these traditions together is their practicality. Star catalogues weren't abstract academic exercises, they were survival tools as vital as a plow or a sail. Whether guiding a ship through a moonless night or telling a farmer when to sow seeds, the stars were humanity's first global infrastructure, an unbroken network of light connecting continents, cultures, and generations. And that's the real wonder. These ancient navigators and farmers didn't just use the stars. They listened to them, learning a language written in light, one that whispered secrets of when to move, when to plant, and when to set sail into the great unknown. Now consider this, if the stars could guide ships and crops with such precision, what else did they teach us? The answer lies in the rhythm of seasons, where astronomy and agriculture met in a dance as old as civilization itself. The same constellations that steered sailors home also told farmers when the Earth was ready to give life, a cosmic partnership we'll explore next. For the ancient Egyptians, the star Sirius wasn't just a bright dot in the sky, it was a lifeline. When it first appeared above the horizon just before dawn, a phenomenon called the heliacal rising, they knew the Nile's floodwaters would soon follow. This wasn't guesswork, it was a precise celestial clock honed over centuries of observation. The entire agricultural cycle, planting, growing, harvesting, revolved around this single astronomical event. Temples were aligned to catch Sirius's first light, and priests kept meticulous records, carving the star's movements into temple walls alongside prayers for fertile soil. Their star catalogues weren't academic curiosities, they were the backbone of a civilization fed by the river's rhythm. Meanwhile, halfway across the world, the Maya were decoding a different celestial pattern. To them, Venus wasn't just a planet. It was Kukulkan, the feathered serpent god whose movements dictated the fate of crops. Their Dresden Codex contains pages of Venus tables so accurate they could predict its appearances 500 years into the future. Why such precision? Because Venus's cycles were woven into their agricultural calendar. When it reappeared as the morning star, it signaled the start of the planting season for maize, the staple of Maya life. A miscalculation could mean famine, so their astronomers tracked Venus with a devotion that bordered on sacred duty. But how did these cultures bridge the gap between stars and soil? The answer lies in their almanac's hybrid texts that blended astronomy, mythology, and practicality. The Babylonians, for instance, didn't just note when the Pleiades rose, they specified which crops to sow that week. Their pinned tablets are essentially farmers' almanacs crossed with star charts, where celestial events are paired with instructions like harvest barley or prepare the irrigation canals. These weren't abstract connections, they were hard-won insights passed down through generations of trial and error. The tools they used to make these observations were often deceptively simple. A shadow stick, for example, could track the sun's path across the seasons, marking solstices and equinoxes with nothing more than a wooden post and a flat stretch of ground. The Chinese developed the gnomon, a vertical rod whose shadow length revealed the sun's altitude critical for determining the solar terms that guided planting. And in the Andes, the Inca used pillars called sucancas to frame the rising sun during key agricultural dates, turning mountain ridges into a sprawling celestial calendar. Yet some methods were astonishingly sophisticated. The Maya likely used crossed sticks as a rudimentary sextant, citing Venus between the gaps to measure its position. The Egyptians built Merkhit's plumb-line instruments to align stars with temple doorways, creating a stone observatory where architecture itself became a measuring tool. These weren't just gadgets, they were extensions of human ingenuity, transforming the night sky into a tool as tangible as a plow or a sickle. What's striking is how universal this practice was. From the rice terraces of China to the milpa fields of Mesoamerica, farmers shared a common language written in the stars. They didn't need telescopes to understand the cosmos. They needed only patience, careful observation, and the wisdom to see that the heavens and the earth were partners in the dance of survival. And as we'll see next, the tools they crafted to read that dance would lay the groundwork for every astronomical instrument that followed. The Antikythera mechanism wasn't just a device, it was a mechanical cosmos in miniature. Discovered in a shipwreck off the coast of Greece in 1901, this 2,000-year-old bronze wonder still baffles scientists today. Inside its corroded casing lay a labyrinth of interlocking gears, some with teeth cut to precise angles, designed to mimic the motions of the sun, moon, and planets. Turn the handle and dials would spin like celestial clockwork, predicting lunar eclipses down to the hour and tracking the 4-year cycle of the Olympic Games. This wasn't just a tool, it was a portable planetarium, a testament to Greek engineering so advanced that nothing rivaling its complexity would appear again until medieval Europe's cathedral clocks. But the real shock isn't just what the Antikythera mechanism could do, it's what it implies. Gears this precise suggest a tradition of mechanical astronomy stretching back centuries before its creation. Who taught the Greeks to build such devices? Some speculate they borrowed from Babylonian water clocks or Egyptian star clocks, technologies lost to time. Others wonder if Archimedes himself, famed for his celestial globe, inspired its design. The unsettling truth, this mechanism might not have been unique. Ancient texts mention similar devices in libraries and temples, all vanished now. leaving the Antikythera as our only surviving clue to a forgotten technological age. Meanwhile, in China, astronomers were crafting their own masterpieces. The armillary sphere, a ringed model of the heavens, wasn't just decorative, it was a precision instrument. By aligning its rotating rings with the celestial equator and ecliptic, observers could measure star positions to within fractions of a degree. The Tang dynasty's Yixing even built one powered by water wheels, creating the world's first mechanical astronomical clock in the 8th century. But here's what's extraordinary. Chinese astronomers didn't just copy Greek ideas. Their spheres used an equatorial coordinate system, different from Ptolemy's ecliptic-based models, proving innovation wasn't confined to one culture. Then there's the astrolabe, the pocket computer of the medieval world. Born in ancient Greece but perfected by Islamic scholars, this handheld marvel could solve hundreds of problems, from telling time to calculating prayer directions, with a twist of its pierced discs. Its secret, stereographic projection, a mathematical trick that flattened the 3D sky onto a 2D plate without distorting angles. Picture a skilled navigator on a moonless desert, holding the astrolabe aloft to align its sights with Polaris. In moments, he'd know his latitude, the time, even the Qibla direction to Mecca. This wasn't just science, it was artistry in brass, blending geometry with daily survival. Yet for all their brilliance, these instruments share a haunting legacy of loss. The Antikythera mechanism spent 2 millennia underwater. Countless astrolabes melted down for their metal. Armillary spheres crumbled in wars or fires. Each surviving artifact is a miracle, a whisper of how much more once existed. And that raises the chilling question: how many star catalogs, how many astronomical breakthroughs vanished with them? The tools we've found hint at a golden age of celestial mechanics far richer than textbooks suggest, one where the line between myth and machinery blurred, and where the heavens weren't just observed but engineered. Now consider the gaps in our knowledge. The Antikythera's eclipse predictions relied on Babylonian Saros cycles, but where are the Greek manuals explaining its use? Chinese records mention clockwork orreries displaying planetary motions, yet none survive intact. These silences in history aren't just absences, they're mysteries, urging us to rethink what ancient astronomers truly knew. Because every time we dig up a device like the Antikythera, it doesn't just answer questions, it rewrites them. The burning of the Library of Alexandria wasn't just a loss of books, it was a cosmic blackout. Within its halls lay star catalogues so detailed, they reportedly tracked celestial movements across millennia, compiled by scholars whose names we'll never know. When the flames consumed the library, they didn't just destroy parchment, they erased entire lineages of observation, like snapping a telescope's lens shut on the ancient world's view of the heavens. But here's what haunts astronomers today. The surviving works of Ptolemy and Hipparchus repeatedly mention earlier sources: Chaldean tablets, Egyptian scrolls, even Persian sky maps that simply vanished. These weren't just references, they were breadcrumbs leading to a deeper understanding of the cosmos, now lost to ash and time. Take the Chaldeans, for instance. Later Greek writers spoke of their star lists with reverence, describing methods so precise they could predict planetary positions centuries in advance. One fragmentary text mentions a star of the god Marduk that modern researchers suspect might have been Jupiter's moon Ganymede, visible only with exceptional eyesight under perfect conditions. Could the Chaldeans have documented celestial bodies invisible to the naked eye? Without the original tablets, we're left reconstructing their knowledge like detectives piecing together a shredded map. Even more tantalizing are the gaps in our planetary records. The Babylonians meticulously logged Venus's cycles, but their tablets say almost nothing about Mercury, a planet so elusive it's missing from many ancient catalogues. Was this omission accidental, or did specialized Mercury observations exist in texts that crumbled to dust? Some scholars point to a single line in a surviving Greek manuscript hinting at a lost Egyptian treatise on Mercury's hidden passages, suggesting entire branches of planetary astronomy may have flourished and faded without leaving a trace. Then there's the mystery of the southern stars. Most ancient catalogues focus on the northern hemisphere, but a handful of references, like a passing remark in Strabo's geography, describe Phoenician sailors mapping southern constellations unknown to Mediterranean astronomers. These water stars, as they called them, guided ships around Africa's coast, but no complete records survive. Were there once star charts spanning the entire sky, lost when maritime trade routes shifted? The question gnaws at historians because every missing catalogue isn't just absent data. It's a broken link in humanity's collective memory of the cosmos. Yet for all we've lost, modern technology is revealing surprises hidden in the catalogues we still have. Take the Dendera Zodiac from Egypt's temple ceiling, long dismissed as mythological art until astronomers realized its star positions precisely matched the sky in 50 BC, proving it was a sophisticated celestial snapshot. Or the recent digital analysis of Ptolemy's coordinates, which uncovered systematic errors suggesting he copied older data without adjusting for precession, inadvertently preserving fragments of a far more ancient catalogue beneath his numbers. These aren't just historical curiosities, they're proof that even our surviving records are palimpsests, with layers of knowledge waiting to be peeled apart. What emerges from these fragments is a humbling truth. Our ancestors saw the sky not as static, but as a living archive. Every star catalogue was a work in progress, amended across generations as new observations refined old truths. The real tragedy of Alexandria's loss isn't just the knowledge burned, it's the conversations cut short, the corrections never made, the celestial stories left half-told. And that's why modern astronomers still scour these ancient texts, not just for what they contain, but for the ghosts of what they've lost, the whispers of observers who, millennia ago, stood under the same stars and dared to measure the infinite. Now consider this, if we've only been working with fragments, how much closer might these civilizations have come to unraveling the cosmos than we ever imagined? The answer lies not in the catalogues we've found, but in the eerie precision of the ones that got away. To test the accuracy of ancient star catalogues, modern astronomers turn the clock back literally. Using advanced software, they calculate how the night sky would have appeared thousands of years ago, factoring in a phenomenon called precession. That's the slow wobble of Earth's axis, which shifts star positions by about 1 degree every 72 years. When they overlay Hipparchus's coordinates from 129 BC onto digital reconstructions, something remarkable happens. Most of his stars land within a hair's breadth of their expected positions. It's as if he handed us a 2,000-year-old map that still works today. But not every catalogue survives scrutiny unscathed. Ptolemy's Almagest, while groundbreaking, contains curious gaps. When researchers compared his star positions to backward calculated models, they found clusters of errors like a group of stars in Aquarius, all offset by the same small margin. This wasn't random noise. It hinted at a scribe's copying mistake centuries ago, where an entire column of data was misaligned. Other discrepancies reveal the limits of ancient tools. Stars near the horizon, distorted by atmospheric refraction, show larger errors, proving even the sharpest-eyed astronomers struggled with the same visual tricks that still challenge stargazers today. The real test comes with variability stars, celestial objects like Algol, whose brightness fluctuates over time. Babylonian tablets describe it as the demon star, noting its periodic dimming. Modern analysis confirms their records match Algol's known cycle almost exactly. How could they detect such subtle changes without photometers? Some scholars suggest they used reference stars, comparing brightness levels night after night with meticulous patience. Others propose ritual observations like tracking stars during religious festivals provided built-in intervals for long-term monitoring. Yet the most telling validations come from cosmic cataclysms. Chinese records of a guest star in 1054 align perfectly with the Crab Nebula's known supernova, while Babylonian eclipse predictions, when adjusted for their local timekeeping, land within hours of modern retrocalculations. These aren't lucky guesses, they're proof of systematic observation spanning generations. But here's the twist: some errors aren't mistakes at all. When Ptolemy's coordinates for Sirius appear slightly off, it's not because he misobserved, it's because the star itself has moved. Modern astronomers can trace its proper motion across the millennia, a subtle drift ancient catalogues inadvertently preserved. In these tiny discrepancies, we don't find failure. We find fingerprints, evidence of real people under real skies, doing their best to measure an infinite universe with nothing but their eyes and their wits. Now consider what these cross-checks reveal about cultural priorities. Why did Ptolemy fixate on certain stars while ignoring others? Why did Chinese astronomers log comets the Greeks dismissed as atmospheric flukes? The answers lie not in the math, but in the myths, politics, and daily needs that shaped how each civilization saw the sky. For the ancient Chinese, the night sky wasn't just a canvas of stars, it was a celestial mirror of their empire. They divided the heavens into constellations that mirrored their earthly bureaucracy, complete with emperors, palaces, and even a marketplace. The purple forbidden enclosure, a region near the North Celestial Pole, housed the celestial emperor's court, flanked by ministers and guards. This wasn't whimsy, it was cosmology as statecraft. When a comet streaked through the prison constellation, court astronomers interpreted it as a sign to review legal cases for injustices. Every star had a role, every celestial event a bureaucratic meaning. Their catalogues weren't just scientific records, they were cosmic policy manuals where the sky's order reinforced the empire's harmony. Half a world away, the Greeks painted a different picture. To them, constellations were epic dramas frozen in light. Orion wasn't just a hunter, he was a boastful giant eternally pursued by Scorpius, his mythical rival. The Milky Way became spilled milk from the goddess Hera's breast, a story that turned a band of faint stars into a divine anecdote. But here's what's fascinating: these myths weren't just decorative. They served as mnemonic devices, helping sailors and farmers navigate by turning abstract star patterns into unforgettable characters. A Greek shepherd could glance at Perseus holding Medusa's head and instantly recall which stars marked the autumn harvest. The sky wasn't just mapped, it was memorized through storytelling. Yet some of the most profound perspectives came from cultures without written catalogues at all. Aboriginal Australians for over 60,000 years have passed down star knowledge through songlines, oral maps where constellations guide journeys across the land. The emu in the sky, formed by dark patches in the Milky Way, isn't just a shape, it signals when to gather emu eggs. When the celestial emu's posture changes, it mirrors the breeding cycles of its earthly counterpart. This isn't astronomy separated from life. It's astronomy woven into survival, where the stars are chapters in an unbroken song that links land, sky, and season. Even within these broad traditions, nuances abound. The Maya saw the Pleiades not as seven sisters, but as the rattles of a celestial serpent, their appearance marking the start of the rainy season. Norse cultures viewed the auroras as the armor of dead warriors, a shimmering reminder of Valhalla. These variations aren't just cultural flair, they reveal how environment shapes cosmology. Desert-dwelling Bedouin navigated by stars that mirrored their nomadic routes, while Polynesian sailors named constellations after ocean currents and fish. The sky became a language, its dialects as diverse as the people beneath it. So why does this tapestry of perspectives matter? Because it reminds us that astronomy has never been a single story. The same stars that guided Chinese emperors also whispered to Maya farmers and Aboriginal elders, each interpreting the cosmos through the lens of their needs and beliefs. This diversity isn't a footnote, it's the heart of humanity's relationship with the heavens. When we compare these catalogues, we're not just studying stars, we're uncovering how cultures turned the night sky into a mirror, reflecting their fears, hopes, and deepest understandings of existence. Now consider how these celestial interpretations bled into another universal practice, astrology. What began as star mapping soon became star reading, as ancient astronomers sought not just to chart the heavens, but to decipher their messages. Astrology and astronomy weren't just neighbors in the ancient world, they were the same discipline. Babylonian priests scanning the heavens for omens weren't stargazers dabbling in mysticism. They were scholars who believed the gods wrote their will in celestial movements. When they noted Venus appearing in a certain constellation, it wasn't just data, it was a divine memo, a warning of droughts or wars. Their star catalogues doubled as cosmic dictionaries, translating planetary alignments into prophecies with the same meticulous precision they used to predict eclipses. The famous Enuma Anu Enlil tablets, for instance, paired astronomical events with earthly consequences. If Mars approaches Scorpius, the king will face rebellion. This wasn't pseudoscience to them, it was statecraft, as vital as modern weather satellites or economic forecasts. The Greeks took this fusion further. Ptolemy's Tetrabiblos, his treatise on astrology, wasn't some fringe text, it was the sequel to his groundbreaking Almagest. To him, the math that mapped star positions also revealed their influence. A planet's geometrical relationship to the zodiac could signal personality traits or geopolitical shifts, all calculated with the same rigor he applied to celestial mechanics. Even Hipparchus, the father of precise astronomy, reportedly wrote astrological works now lost to time. The line between science and superstition didn't just blur, it vanished entirely. But change crept in through patience and proof. Islamic astronomers like al-Biruni in the 11th century began questioning astrological claims, noting that identical planetary alignments often preceded wildly different events. By the Renaissance, Tycho Brahe's ultra-precise star maps, created to refine horoscopes, ironically exposed inconsistencies in astrological predictions. Kepler, who cast horoscopes for royalty, privately grumbled about the fool's errand of linking stars to fate, even as his laws of planetary motion unwittingly dismantled the very system he served. Yet astrology's fingerprints never faded. The zodiac constellations we recognize today, Aries, Taurus, Gemini, are direct descendants of Babylonian star lore, their boundaries fixed by ancient observers who saw mythic animals and heroes in the night. Modern astronomy may have stripped them of prophetic power, but their names endure, a poetic echo of humanity's first attempts to find meaning in the stars. Religion's role in this celestial storytelling runs even deeper. From Egyptian temples aligned to Sirius to Inca priests tracking solstices at Machu Picchu, the heavens weren't just studied, they were worshipped. Sacred architecture became astronomical instruments, and gods wore constellations like crowns. When we peel back the layers of these star catalogues, we're not just uncovering science, we're reading prayers etched in light. To the ancient Egyptians, the stars weren't just lights in the sky, they were the skeletal remains of gods. The constellation Orion mirrored Osiris, god of rebirth, his belt stars aligning with the pyramids at Giza in a celestial blueprint of resurrection. When priests timed rituals by Sirius's rising, they weren't merely observing nature, they were participating in the goddess Isis's annual mourning for her husband Osiris, a cosmic drama that promised renewal for all. Their temples became stone observatories, with narrow corridors designed to catch the first gleam of dawn on a pharaoh's coronation day, turning architecture into a sacred clockwork mechanism. The Maya took this celestial devotion even further. Their pyramid at Chichen Itza isn't just a line to the equinoxes, it's a divine calculator. During the spring equinox, shadows slither down the steps like the feathered serpent god Kukulkan descending to Earth, a phenomenon so precise it could only have been engineered by astronomers who tracked the sun's path for generations. Their star catalogues weren't academic exercises, they were ritual scripts dictating when to conduct bloodletting ceremonies or crown new kings based on Venus's position. A ruler's legitimacy depended on his astronomer's ability to predict celestial events, making sky watching a matter of political and spiritual survival. But why did religion dominate early astronomy so completely? The answer lies in humanity's oldest quest to find order in chaos. When Babylonians saw Mars reverse course in the sky, they didn't just record the motion, they interpreted it as the god Nergal turning his fiery gaze toward Earth, demanding sacrifices to avert disaster. This wasn't primitive superstition, it was pattern recognition fused with meaning-making. By attributing celestial phenomena to divine will, cultures transformed random cosmic events into a comprehensible narrative, one where human actions could influence heavenly outcomes through prayer, ritual, or moral conduct. The Inca demonstrated this perfectly at Machu Picchu. Their Intihuatana stone, carved to catch the sun at solstices, wasn't merely a calendar, it was a hitching post for the sun, designed to literally tie the sun god Inti to the earth during the critical planting season. When Spanish conquistadors later destroyed similar stones across Peru, they weren't just smashing rocks, they were severing an entire cosmology that had sustained Andean civilization for centuries. This spiritual hunger left its mark in stone across the globe. Newgrange in Ireland, a 5,000-year-old tomb, channels the winter solstice sun through a narrow passage to illuminate its inner chamber, a feat requiring generations of astronomical observation. At Angkor Wat, the central towers align so precisely with the equinox sun that modern scholars suspect the entire temple complex might be a scaled-down model of the Hindu cosmos, with its towers representing Mount Meru, the axis of the universe. What united these sacred sites wasn't just their precision, but their purpose. Unlike modern observatories designed for detached study, ancient astronomical architecture blurred the line between science and worship. The same priests who calculated star positions composed hymns to celestial deities. The same hands that carved alignment markers also offered sacrifices. For them, understanding the heavens wasn't about cold objectivity, it was about communion with forces greater than themselves, a dialogue written in stone and starlight that still whispers to us across the centuries. Now consider this, when modern astronomers point telescopes toward distant galaxies, they're continuing humanity's oldest tradition, not just mapping the cosmos, but seeking their place within it. The tools have changed, but the longing remains the same. Stonehenge's towering stones don't just stand in a circle, they form a celestial clockwork. At dawn on the summer solstice, sunlight slices perfectly between the pillars, illuminating the altar stone like a spotlight. This wasn't accidental, it was precision engineering on a scale that still baffles archaeologists. the builders didn't just know the sun's yearly path, they encoded it in stone, aligning the monument to mark the longest day with jaw-dropping accuracy. But here's what's even more remarkable. Recent studies suggest some of Stonehenge's lesser-known pits align with major lunar standstills, events that occur only once every 18.6 years. How did Neolithic farmers without writing or advanced tools track a cycle that long? The answer might lie in generations of oral tradition, where star lore passed down through songs and stories became as precise as any modern ephemeris. Across the Mediterranean, the Great Pyramid of Giza whispers its own celestial secrets. Its sides align almost perfectly with the cardinal directions north, south, east, west, with an error margin of just 1/15 of a degree. To achieve this, the builders likely used the stars. One theory suggests they tracked the circumpolar stars Kochab and Mizar, which around 2500 BC would have appeared to pivot around true north like a cosmic plumb line. But the pyramid's air shafts add another layer of mystery. Two narrow tunnels from the king's chamber point directly to Orion's belt and the pole star of that era, as if the pharaoh's soul needed a roadmap to the heavens. Were these alignments symbolic, navigational, or both? The debate rages on, but one thing's clear: the stars didn't just inspire these builders, they guided their chisels. Further south, in the jungles of Cambodia, Angkor Wat's western gate aligns with the spring equinox sun in a way that turns the entire temple into a solar observatory. On that morning, the sun rises directly over the central tower, a phenomenon so precise it could only result from meticulous astronomical planning. But Angkor's architects didn't stop there. Recent LiDAR scans reveal an invisible grid of canals and roads mirroring the Draco constellation, suggesting the city itself was a terrestrial echo of the cosmos. This wasn't just architecture, it was sacred geometry where every brick and moat reflected a celestial blueprint. The methods behind these feats remain hotly debated. Some scholars argue for simple but effective tools like the Merkit, an Egyptian forked stick used to sight stars. Others propose that trial and error over centuries refined alignments, with each generation correcting the last's observations. But the most tantalizing theory involves lost technologies, devices like the Greek dioptra or Chinese gnomon, capable of measuring angles with surprising precision. Whatever their tools, these builders shared a common philosophy. The earth and sky were mirrors, and their structures were bridges between them. What unites Stonehenge, the pyramids, and Angkor Wat isn't just their celestial ties, it's their cultural weight. These weren't vanity projects, they were the beating hearts of civilizations where astronomy shaped identity, power, and faith. When a Babylonian ziggurat aligned with Venus or a Maya temple echoed the Pleiades, it declared that heaven and earth were partners in a grand design. And that raises a provocative question. If men with stone tools could achieve such precision, what does that say about our modern disconnect from the stars? Now let's turn to a group often overlooked in the annals of astronomy. The women who mapped the heavens alongside kings and priests, their contributions hidden in the shadows of history, but no less vital to the story of the stars. History books love to celebrate the great male astronomers Ptolemy, Hipparchus, but scratch beneath the surface, and you'll find women shaping celestial knowledge in every era. Take Hypatia of Alexandria, the 4th century scholar who didn't just study the stars. She built astrolabes and wrote commentaries on Ptolemy's work that became standard texts for centuries. Her murder by a mob in 415 CE wasn't just a personal tragedy. It symbolized the violent suppression of intellectual freedom, especially for women. Yet fragments of her star charts survived, tucked into the margins of later manuscripts, proof that her voice couldn't be fully erased. Half a world away, in 18th century China, Wang Zhenyi defied even stricter norms. At a time when most women were confined to domestic life, she climbed observatory towers to track lunar eclipses, publishing papers that corrected male scholars' miscalculations. Her poem, disputing the rotundity of the Earth, wasn't just literature. It was a sly manifesto, using verse to explain planetary motion to those denied formal education. Like Hypatia, her legacy was nearly buried until a single handwritten astronomy manual surfaced in a Beijing archive 2 centuries later, its pages filled with her precise planetary calculations. But why are these stories so rare? The answer lies in the quiet erasure of women's labor. Babylonian temple records list female scribes tracking Venus, but their names were often omitted from royal chronicles. Medieval European convents housed nuns who produced illuminated star calendars, yet their work was attributed to male clerics. Even when women like the Venetian mathematician Elena Cornaro Piscopia earned university degrees in the 17th century, their astronomical treatises were published under male pseudonyms or labeled as curiosities rather than scholarship. Yet traces persist in unexpected places. A 9th century Persian manuscript praises the astronomer Maryam al-Astrolabe, who refined the astrolabe's design, making it portable enough for traders and pilgrims. In India, the Rigveda's hymns to the stars, composed around 1500 BCE, are traditionally credited to the female sage Ghosha, suggesting early Vedic astronomy might have had women's voices woven into its foundations. These aren't just footnotes, they're proof that celestial knowledge was never exclusively male. The real tragedy isn't just the loss of their work, it's the distortion of history itself. When we forget Hypatia's star charts or Wang Zhenyi's eclipse predictions, we don't just overlook individuals, we miss the collaborative nature of ancient science. Astronomy wasn't built by lone geniuses but by networks of thinkers, many of whom history rendered invisible. Rediscovering these women isn't about political correctness, it's about restoring the true story of how humanity mapped the heavens, one observation at a time. Now consider this: if women like Hypatia could measure star positions with such accuracy using only naked eye tools, how did ancient astronomers rank stars by brightness long before telescopes? The answer lies in a system so intuitive, it's still used today, but with secrets modern skywatchers often overlook. Long before the invention of photometers or digital sensors, ancient astronomers developed an uncanny ability to rank stars by brightness with nothing but their eyes and sheer observational discipline. Take Ptolemy's Almagest, which meticulously categorized over 1,000 stars into 6 distinct magnitudes, a system so intuitive it still underpins modern astronomy. The brightest stars like Sirius or Vega anchored the first magnitude, while the faintest visible to the naked eye settled into the 6th. But here's what's astonishing. When modern astronomers compared these ancient rankings to today's photometric measurements, they found Ptolemy's classifications matched with striking consistency. How did he achieve such precision without a single lens or light meter? The answer lies in a technique as simple as it was ingenious: comparative observation. Imagine an astronomer on a clear Babylonian night, holding up a hand to block the moon's glare while shuffling their gaze between 2 stars. By repeatedly contrasting one against another, like placing Spica next to Arcturus, they could assign relative brightness tiers. Some cultures took this further, using natural reference points. The Chinese, for instance, noted when a star became visible at dusk or dawn, using atmospheric conditions as a natural filter to gauge intensity. A star that pierced the twilight first was clearly brighter than one only seen in full darkness, but the real masterstroke was institutionalizing these observations. Greek and Babylonian astronomers didn't work in isolation. They built consensus across generations. If one observer called Aldebaran a first-magnitude star, others would verify it through communal observation, creating a living database refined over centuries. This collaborative approach minimized individual biases like variations in eyesight or local atmospheric conditions, turning subjective judgments into remarkably objective data. What's often overlooked is the cultural diversity in these systems. While the Mediterranean world favored 6 tiers, Hindu astronomers in India developed a 5-level classification, and Polynesian navigators spoke of leading stars that outshone others by consistent margins. These weren't arbitrary choices, they reflected practical needs. A sailor relying on stars to cross the Pacific didn't need exact magnitudes, just unambiguous brightness hierarchies to steer by. The legacy of these ancient brightness scales is more than historical curiosity. When 19th-century astronomers formalized the modern magnitude system, they didn't start from scratch, they built on Ptolemy's framework, proving that human eyes, trained by patience and rigor, could rival early instruments. That's the real lesson here. Precision doesn't always require technology. Sometimes it's born from generations of looking up, comparing, and remembering. An unbroken chain of curiosity stretching back to the first time someone squinted at the sky and asked, which one shines brighter? As these star catalogues passed into the hands of Renaissance scholars, they didn't just preserve knowledge, they ignited a revolution. The same brightness rankings that guided Greek sailors would soon help Galileo challenge the heavens themselves, proving that the stars had more to say than anyone had dared to imagine. The dusty shelves of medieval European monasteries held more than just religious texts, they cradled the seeds of a cosmic revolution. When scholars in 12th century Toledo began translating Arabic manuscripts salvaged from the fallen libraries of Baghdad and Cordoba, they weren't just recovering lost knowledge, they were waking a slumbering giant. Among these treasures were star catalogues like Ptolemy's Almagest, preserved and refined by Islamic astronomers over centuries. Suddenly, European thinkers had access to celestial coordinates precise enough to track planets backward and forward in time, a mathematical time machine that revealed flaws in the old Earth-centered cosmos. Copernicus, poring over these texts in a Polish cathedral tower, noticed something unsettling. Ptolemy's intricate system of epicycles, those looping planetary paths meant to preserve Earth's central place, required constant tweaks to match observations. The ancient data itself hinted at a simpler truth. What if the Sun, not Earth, anchored the dance of the planets? His revolutionary De Revolutionibus didn't spring from nowhere. It grew from centuries of accumulated observations, passed down through Greek, Persian, and Arabic hands. The real breakthrough wasn't rejecting ancient astronomy, it was reading it with fresh eyes, uncovering patterns its creators never imagined. Kepler took this further. Armed with Tycho Brahe's ultra-precise star maps themselves descendants of Hipparchus's methods, he found that planets moved in ellipses, not perfect circles. Those elegant curves solved mysteries that had plagued astronomers since Babylon. But here's the twist, Kepler's laws didn't invalidate the old catalogues, they revealed their hidden logic. When he compared his models to star positions recorded in Ptolemy's Almagest, the numbers aligned with eerie precision. The ancients had mapped the symptoms of cosmic order, Kepler diagnosed the disease. This revival wasn't just about science, it was about liberation. For the first time in centuries, European astronomers dared to question not just how the heavens moved, but why. The same star charts that once reinforced dogma became tools for dismantling it. When Galileo turned his telescope to Jupiter's moons in 1610, proving celestial bodies could orbit something other than Earth, he stood on the shoulders of observers who'd tracked those same points of light for millennia without lenses. Their patient records gave him the confidence to defy tradition, knowing the stars themselves backed his claims. Yet while Europe rediscovered these texts, other cultures had never lost their celestial traditions. Indigenous astronomers across the Americas, Africa, and the Pacific were weaving sky knowledge into daily life with equal sophistication, often without written catalogues. The Maori of New Zealand navigated the Pacific by the rising of Matariki, the Pleiades, whose appearance marked the new year and signaled when to plant crops. In North America, the Pawnee built Earth lodges aligned to the morning star, weaving planetary movements into creation stories that doubled as agricultural calendars. These weren't primitive myths, they were living star catalogues preserved through oral tradition and ritual. What unites these threads, the rebirth of classical astronomy in Europe and the unbroken sky traditions of indigenous peoples, is their shared humanity. Whether etched on clay tablets or sung around campfires, star knowledge has always been more than data. It's a compass, a clock, a mirror reflecting our deepest questions. And as we'll see next, that mirror holds surprises even modern telescopes are only beginning to reveal. Polynesian navigators didn't need compasses or star charts. They had the ocean itself as a classroom and the night sky as their textbook. Picture a double-hulled canoe cutting through Pacific swells under a sky so vast it seems to swallow the horizon. The navigator, trained from childhood, reads the stars like street signs. He knows that when the rising of Pleione, a faint star in the Pleiades cluster, aligns with a particular palm tree on a distant atoll, it marks the turning point toward Tahiti. This wasn't guesswork, it was precision astronomy passed down through chants and stick charts, where twigs represented currents and shells marked stars. The Polynesian star compass divided the horizon into 32 directional houses, each anchored by celestial markers. To drift off course meant vanishing into the endless blue, so their knowledge wasn't just tradition, it was survival. Meanwhile, on the plains of North America, the Pawnee people wove the stars into the very fabric of their earth lodges. The morning star, Venus, wasn't merely a celestial object, it was the god Taroa, whose movements dictated the timing of sacred ceremonies. Their villages were laid out as mirror images of the heavens, with lodges positioned to reflect constellations like the Corona Borealis. When skiddy Pawnee priests tracked the path of Mars through the Council of Chiefs, Astrism, they weren't just observing, they were conducting celestial diplomacy, interpreting planetary conjunctions as messages from the spirit world. Unlike Greek astronomers who sought geometric patterns, the Pawnee saw the sky as a storyboard, where every meteor shower or eclipse advanced a narrative older than memory. Aboriginal Australians took this celestial storytelling even further. For over 60,000 years, their songlines' oral maps encoded in music and art linked star patterns to landmarks across the continent. The emu in the sky, formed by dark patches in the Milky Way, wasn't just a constellation, it was a seasonal alarm. When its neck stretched fully in the April sky, it signaled the start of emu egg gathering. The Yolngu people of Arnhem Land still use the rising of the shark constellation, Badum, to predict winds that bring shoals of fish. These traditions weren't static, they evolved over millennia, with elders refining observations across generations. What makes these oral catalogues so extraordinary is their accuracy. When modern astronomers compared Polynesian star paths to GPS data, they found errors of less than 1 degree over 1,000-mile voyages. Pawnee predictions of Venus's cycles aligned with NASA ephemerides to within days. Aboriginal eclipse records embedded in Dreamtime stories match celestial events dating back 40,000 years. This precision shatters the myth that science requires writing. It only requires rigor, and these cultures had it in abundance. the real revelation here isn't just the diversity of star knowledge, it's how it redefines the history of astronomy. For centuries, Western scholars framed scientific progress as a straight line from Babylon to Greece to Europe, ignoring thriving traditions elsewhere. But Polynesian navigators were crossing oceans using stellar dead reckoning while Europeans still feared falling off the Earth's edge. The Maya calculated Venus's synodic period to within seconds per year, a feat unmatched in medieval Europe. Aboriginal skywatchers tracked variable stars like Betelgeuse long before Tycho Brahe coined the term nova. This global tapestry of astronomy forces us to ask, what counts as a star catalogue? Is it only clay tablets and parchment, or can it be a navigator's chant, a Pawnee priest ceremony, or a songline etched in the red desert sand? The answer rewrites history, revealing a cosmos mapped not in one language, but in hundreds, each as precise, as vital, as any entry in Ptolemy's Almagest. Now consider the Zodiac, the 12 constellations that have guided farmers, astrologers, and kings for millennia. Its roots stretch back to Babylon, but its branches reach further than you might think. The Babylonian sky wasn't just a canvas of stars. It was a cosmic calendar carved into 12 equal slices, each ruled by its own constellation. Around 500 BCE, their priests meticulously divided the ecliptic, the sun's yearly path, into 12 30-degree segments, creating the first zodiac. But this wasn't astrology as we know it today. It was agricultural mathematics. When the sun entered the hired man sector, later Aries, it signaled barley harvest time. The Great Twins, Gemini, marked the start of the dry season. Each slice wasn't just a star group. It was a celestial almanac tying celestial motion to earthly survival. The Greeks inherited this system but added something revolutionary: mythology. By renaming the Babylonian Pabilsag as Sagittarius the Archer and the Scales as Libra, they turned star clusters into storytelling constellations. Suddenly, the zodiac wasn't just a farmer's tool. It was an epic written in light, where heroes and monsters played out eternal dramas. Ptolemy cemented this fusion in the Almagest, using the zodiac as the backbone for his star catalogue. Yet the real genius lay in its flexibility. Unlike rigid celestial grids, the zodiac's 12-part structure could absorb cultural interpretations, from Hindu nakshatras to Chinese animal signs, while keeping its core mathematical integrity. What's often overlooked is the zodiac's hidden precision. Those 30-degree divisions weren't arbitrary. They matched the sun's monthly movement with uncanny accuracy. Babylonian astronomers knew that dividing 360 degrees by 12 gave clean, workable units, a system so practical that even NASA uses zodiacal coordinates for spacecraft navigation today. But here's the twist: the constellations themselves are uneven. Scorpio sprawls across 33 degrees, while Cancer barely covers 20. The zodiac's endurance comes from ignoring these irregularities, focusing instead on the mathematical scaffold beneath. Modern horoscopes, for all their pop culture gloss, still lean on this ancient framework. When your daily forecast mentions Taurus season, it's referencing the same solar position that Babylonian scribes recorded on clay tablets 3 millennia ago. The difference, where they saw planting cycles, we see personality traits, a testament to how humanity projects its needs onto the stars. Now, let's decode the math that made these celestial divisions possible. Imagine standing under the clear Mesopotamian night, tracing the sun's invisible path backward through the stars. The key tool, the gnomon, a simple stick whose shadow lengths at noon, revealed the sun's shifting position against the zodiac's backdrop. By tracking these angles over years, Babylonian astronomers could predict solstices within hours, their calculations refined by generations of temple scribes. This wasn't mysticism, it was celestial bookkeeping where every shadow and star position was a data point in history's first long-term sky survey. The Babylonians didn't just watch the stars, they turned them into numbers. Their base 60 numeral system, etched into clay tablets with wedge-shaped cuneiform, didn't just count time, it sliced the heavens into measurable arcs. Why 60? Because it's divisible by 12, perfect for tracking the 12 zodiac constellations, and by 30, mirroring the moon's monthly cycle. This wasn't arbitrary math, it was celestial poetry translated into fractions. When they calculated Venus's 8-year cycle or predicted lunar eclipses, they didn't use abstract formulas. They relied on step-by-step algorithms, like a modern cookbook, where each line of cuneiform instructed scribes to add 5, multiply by 3, subtract the previous result. These weren't just equations, they were recipes for decoding the gods' handwriting. Hipparchus took this further by inventing trigonometry, not as abstract theory, but as a stargazer's toolkit. Picture him on the shores of Rhodes, measuring the angle between the moon and the star speaker to calculate their distance. Without calculators or log tables, he relied on chord tables, pre-computed lengths corresponding to angles, a brute force method that required armies of scribes crunching numbers for months. His breakthrough wasn't just accuracy, it was scalability. By breaking the sky into triangles, he could extrapolate star positions he'd never directly observed, turning scattered data points into a predictable grid. The real marvel lies in their error correction. Babylonian tablets often include 2 sets of calculations, one rough, one refined, showing scribes cross-checking their work like modern scientists peer-reviewing papers. When Greek astronomers found discrepancies in old star charts, they didn't dismiss them as mistakes. They recalibrated entire coordinate systems, proving ancient science was a living, self-correcting discipline. What's often overlooked is the physical labor behind these feats. A single planetary position might require 50 iterative calculations, each scratched onto wax tablets or papyrus. The Library of Alexandria's scribes didn't just copy texts, they verified numbers, sometimes annotating margins with notes like, "This value seems too large," or "check against the summer solstice." This was astronomy as endurance sport, where progress depended on human persistence as much as genius. Yet for all their precision, these methods held mysteries. Some Babylonian eclipse predictions hit the mark centuries later, suggesting they'd discovered long-term cycles modern science still can't fully explain. Hipparchus's star coordinates occasionally show errors too consistent to be accidental, hinting he might have inherited data from even older, lost sources. These aren't flaws, they're breadcrumbs leading us to deeper questions about how much the ancients truly knew. Their legacy isn't just in the answers they left, but in the questions they teach us to ask. When a Babylonian scribe tracked Jupiter's path or Hipparchus mapped the equinox's slow drift, they weren't just solving problems. They were inventing the very idea that the cosmos could be understood through numbers, a revolution that echoes every time a modern telescope captures light from a galaxy billions of years away. Now, let's cross the Atlantic, where Maya astronomers painted their star catalogues in jade and blood, proving the language of the heavens wasn't confined to clay and parchment. In the rainforests of Mesoamerica, the sky wasn't just observed, it was woven into the very stones of towering pyramids, a testament to a cosmology as precise as it was profound. The Dresden Codex isn't just an ancient book, it's a celestial calculator written in bark paper and jaguar skin glue. Flipping through its weathered pages, you'll find Venus tables so precise they could predict the planet's appearances 500 years into the future with an error margin of just 2 hours. Imagine Maya astronomers perched atop pyramid observatories like El Caracol, their eyes fixed on the horizon as Venus emerged from the dawn light. To them, this wasn't just a planet, it was Kukulkan, the feathered serpent god whose movements dictated when to plant corn, wage war, or crown kings. Their calculations weren't abstract math, they were survival codes woven into the very fabric of empire. What's staggering is how they achieved this without telescopes or written numerals. The Maya used a base 20 counting system, tracking time in nested cycles that interlocked like cosmic gears. The long count calendar measured epochs of 5,125 years, while the Tzolk'in and Hob cycles, 260 and 365 days respectively, meshed to create a 52-year calendar round. Venus's 584-day cycle slid perfectly into this machinery, its reappearances marked by notches in stone stelae and painted almanacs. But the real genius lay in their corrective math. When they noticed their predictions drifting, they added leap days to sync with celestial reality, a concept Europe wouldn't adopt for centuries. The Aztecs, inheriting this tradition, gave constellations mythic identities that guided daily life. Their fire drill constellation, likely part of Orion, wasn't just stars. It was the tool used by gods to ignite the sun at the dawn of time. The Milky Way became Mixcoatl, the cloud serpent whose path across the sky mirrored the journey of souls. These weren't bedtime stories, they were mnemonic devices, turning the sky into a memory palace where every star cluster held practical meaning. The Codex Mendoza even depicts Aztec children learning star patterns as part of their education, proving astronomy was as essential as farming or warfare. El Caracol, the Maya's spiral-shelled observatory at Chichen Itza, stands as a testament to their architectural ingenuity. Its narrow windows align with Venus's extreme positions on the horizon, while the staircase points to the sunset on the spring equinox the same day the pyramid's shadow creates a serpent slithering down its steps. This wasn't just decoration, it was a stone computer designed to amplify human observation with geometric precision. Recent LiDAR scans reveal hundreds of similar structures hidden beneath jungle canopies, suggesting a vast network of celestial monitoring stations. What set Mesoamerican astronomy apart was its visceral connection to time. Where Old World calendars marked seasons, the Maya saw time as a living force, with each day carrying unique spiritual weight. The Dresden Codex's eclipse warnings weren't just scientific forecasts, they were survival guides predicting moments when the sun god might falter and require human intervention through bloodletting rituals. This fusion of math and mysticism created a cosmology where every celestial event was both measurable and sacred, a duality modern science often struggles to comprehend. Now consider the broader implications. While Ptolemy's work survived through meticulous copying, Maya codices were nearly erased by Spanish conquistadors. Only 4 major Maya books remain, salvaged from bonfires of pagan texts. The Dresden Codex survived only because a librarian mistakenly sent it to Europe as a curiosity. What else might those lost books have contained? Some scholars speculate they held Mars tables rivaling the Venus charts, or records of supernova visible only in the clear Mesoamerican skies. The surviving fragments whisper of a system as sophisticated as anything from Babylon or Greece, proof that human curiosity under the same stars sparks similar brilliance, no matter the continent. As we turn from star catalogues to their most practical application, remember this: for the Maya and Aztecs, the sky wasn't just a clock. It was the heartbeat of creation itself, pulsing in time with human destiny. Their observations didn't just track time, they sought to harmonize with it, a quest that would echo in timekeeping traditions from sundials to atomic clocks. Long before the tick of a clock or the chime of a bell, humanity kept time by the silent dance of the stars. The Egyptians didn't just gaze at the night sky, they sliced it into a celestial clock face. Every 10 days, a new star group or decan would rise just before dawn, marking the start of another week. 36 decans divided the year into tidy segments, each star's appearance synchronized with the Nile's flood cycles. Priests in temple observatories would watch for Sirius's heliacal rising the moment it first peaked above the horizon at sunrise, an event so precise it heralded both the new year and the coming floods. This wasn't just poetry, it was precision engineering written in light, where the heavens dictated the rhythm of daily life from planting to harvest. Meanwhile, in China's imperial courts, astronomers tracked time by the 28 mansions, a system dividing the sky into lunar stations. Each mansion corresponded to a specific day of the moon's journey, with key stars acting as celestial hour hands. The star Antares, known as the heart of the dragon, signaled the summer solstice when it aligned with the meridian. Emperors timed coronations and sacrifices to these alignments, believing earthly power waxed and waned with the star's approval. The Tang dynasty even employed water clocks, but these were calibrated nightly against star transits, proving that even their mechanical timepieces bowed to celestial authority. What made star clocks so universal? The answer lies in their flawless reliability. Unlike sundials, useless on cloudy days or at night, stars were visible in all seasons. Their movements were predictable down to the minute over centuries, unaffected by human error or political upheaval. The Babylonians knew that the Pleiades rising in May meant the rivers would soon swell, just as the Polynesians used Orion's belt to navigate monsoon shifts. This wasn't just observation, it was symbiosis, where cultures attuned their survival to the cosmos's unerring tempo. The legacy of stellar timekeeping pulses through our modern calendars. Rome's Julian calendar, reformed by Caesar in 45 BC, borrowed heavily from Egyptian decanal astronomy, fixing the year at 365¼ days, a figure derived from star cycles. Even today's leap year traces back to Hipparchus's realization that star positions drifted over centuries, requiring occasional correction. The week itself may owe its 7-day structure to Babylonian astrologers, who assigned each day to one of the 7 visible planets, including the sun and moon. Yet for all their precision, these systems held tantalizing quirks. Egyptian star clocks worked flawlessly at Thebes but required adjustment further north, an early recognition of latitude's effect on astronomy. Chinese records occasionally note guest stars, supernova, disrupting predictable celestial patterns, forcing astronomers to recalibrate entire timelines. These weren't failures, they were proof of ancient science's adaptability, a willingness to revise models when the stars themselves defied expectations. Now consider the implications. When an Incan priest marked the winter solstice by sunlight striking a carved stone, or a Babylonian scribe logged Jupiter's retrograde motion, they weren't just tracking time, they were building the first frameworks of empirical science. Their star catalogues became the bedrock for navigation, agriculture, and even architecture, with monuments like Stonehenge serving as monumental timekeepers. This cosmic chronometry did more than measure hours, it shaped civilizations, turning the chaos of human existence into rhythms as predictable as Sirius's return. As we shift from the dependable clocks of the sky to the irregularities hidden in ancient star catalogues, a question lingers. If the heavens were humanity's first timepiece, why do some records contain impossible data, coordinates too precise for their era, or stars that shouldn't have been visible? The answers may lie not in the stars themselves, but in the lost technologies and forgotten methods of those who mapped them.